All right, everyone, welcome to the first screencast for Chapter 5. So in this screencast, we're going to kind of finally take a look at what it is we need to do when we have endogeneity. So basically, if there is a left out variable z that is correlated with x and y, what are the steps that we need to take in order to fix that? All right. So here's kind of an example to get us started. So we've been tasked with trying to figure out how sales respond to temperature. So this could be like a retail store. So the boss came up and said, hey, I want you to see if our sales are affected by temperature at all. And so your dependent variable is the sales in billions of dollars during month T. So notice that the subscript here is a T. That indicates that the unit of analysis here, the rows in our data set are time periods, months, all right? T is for time period. And then the independent variable is temperature, the average temperature in a given month. So we're going to see how does a 1 unit increase in the average temperature in a given month affect sales in that month, all right? So it's still just a bivariate regression, all right? So here is a scatter plot that looks at that. So so we see the best fit line here. We see our intercept, and we see the slope here. It's a slightly negative slope going through the scatter plot. And we notice something here. We see these observations that are kind of out of the way of the rest of them. Maybe they're outliers of sorts, but we'll see what's going on there in just a second. And so the beta 1 hat is negative, implying that increasing temperature decreases sales, right? So I don't know the exact slope there off the top of my head, but that's what that would imply. So people shop less as temperature rises. A 1 unit increase in temperature leads to a decrease in sales. But here is where we're gonna, the rubber's gonna hit the road here for us in this chapter. Could there be endogeneity? Could there be another variable correlated with both temperature and sales that could be affecting our results here? And if we leave it out, we would be biased, right? So that's what we're going to take a look at, and that's going to be our question. Well, it's been our question really since the beginning of the semester, but it's going to be our question going forward. Is there such a variable, and if so, what do we need to do about it? So we're going to learn how to control for these other types of variables, and this is the language that we use in econometrics. We're going to say that those z's, those omitted variables that are correlated with x and y, we're going to pull them into the model, and we're going to call them control variables, all right? So this is going to, the technique is now going to be called multivariate OLS. So before it was bivariate OLS, we just had one x and one y right here. So we just have one dependent variable, one independent variable. It's a bivariate regression, two variables. Now we're going to have a multivariate regression. So, and that the tool works basically the same. It's still going to be fitting a line through a scatter plot, but the scatter plot's going to be a little bit different this time. So multivariate OLS refers to OLS with multiple independent variables. We're going to add control variables to the OLS model that we've been developing since the beginning of class. All right. We're going to gain two things. The big deal is we're going to reduce bias, right? Remember, bias was when bias was when we had a distribution and it was not actually centered on the truth. So this is an unbiased distribution of beta 1 hat. A biased distribution would be when maybe the beta 1 hat was over here instead of being here. So this would be a biased distribution. If we have endogeneity, if we've left out a third variable correlated with our x and y, then we get that sort of bias. All right, so, and then the next thing that we gain is we're going to increase precision because we're going to reduce uncertainty, and we'll see that what that will do is that will shrink this beta 1 hat distribution. So it will make this a little bit smaller than it otherwise would be. That's the goal for this section. So here we go. So let's take back up this same scatter plot, but notice what I've done here is I've highlighted all of the Decembers, right? This is multiple years worth of monthly data. And we have the average temperature in Fahrenheit, and we have the monthly retail sales in billions of dollars. And what I've done here is I've just recoded the shape for the months that are Decembers. All right, and notice all of the Decembers are clustered up here in the top of the graph. So there's something going on here with Decemberness. And of course, we all probably know what that is. I managed a toy store throughout undergrad. That was my job to pay for college. And December is, of course, where most of our retail sales happen. So December has a large amount of retail sales because of the holiday shopping season, right? So the average sales are around $11 billion in December, but the average for the other months is $6 billion. So it looks like there's something going on here with December that might be throwing us off, all right? Decemberness, in other words, is correlated with both being cold and it's correlated with sales. So we have a missing Z correlated with X and Y. So what if we controlled for that December effect? The way we're going to do this in our model is not going to be exactly what I describe here, but this is a good way to start to think about what we mean for controlling, all right? So we could control for Decemberness, right? Each month, the Decemberness is what is correlated with X and Y. We could do that by just subtracting the $5 billion difference. And where does that come from? Well, the average sales in December are 11 billion, and the average sales in all the other months is 6 billion, so that's a $5 billion difference. So in order to start to think about what it would mean to control, we could say, well, let's just subtract $5 billion from each of these triangles, right? Pulling it down on the y-axis. So here's what that would look like if we did that. So here we see that now the December months fit the similar pattern as all of the other months. All right, so by controlling for the Decemberness now, maybe we would get a better estimate of the effect of temperature on sales in and of itself, right? Because that's what we want to know. As the temperature goes up by 1 degree, what does that do to sales? We're not interested in Decemberness, but Decemberness is biasing our results in this original graph right here, this original OLS. This Decemberness is probably distorting the slope that we get. All right, so again, this isn't mathematically what we do. We're not literally pulling down the data like that. We're not going to mess with the data, but it is a way to think about what we are going to do. All right. So here are the results of two different regressions, one where December has been included in the model. So in a sense, what we've done is we've now added a control variable here. So let me just mark this out, and we'll just do beta 2 December. So if a month is a December, then it gets a 1 for that variable. And if the month is and this is December sub t, right? Because each of the variables gets a t. So remember, our data set is like this, and each variable. And so this could be sales, right? This would be temperature, and then this is Decemberness. And so for every month that's a December, it gets a 1. All the other months get a 0 all the way through the data set. So this is going to be what the model looks like. So here I am back with the results of that model. So this is the one that doesn't have December. And so this is a pretty common way of displaying multiple OLS regressions that have some of the same variables, but not always. So this, these results, this model has all of these variables, both temperature and December. And this bivariate doesn't have December. That's why you don't see anything there in for December. So without the control for Decemberness, a 1 unit increase in temperature, the average temperature in Fahrenheit for a month, decreases sales by $0.019 billion. And first, is it statistically significant? Yes, T is above 1.96 or T is above 2. So this is a statistically significant effect. So then we can interpret it in the way that I just did. All right. So what happens when we add the control for dissimilarness? Because this is a biased result over here for bivariate. This beta 1 hat is biased. We can't trust it because we know there is a Z dissimilarness that's correlated with both X temperature and Y sales in billions of dollars. So over here, we've now controlled for dissimilarness. Now, we don't really care too much about this slope coefficient because we're not interested in the effect of December on sales. That wasn't our question. This is the slope coefficient we're interested in, this information up here. So first of all, is it statistically significant? Yes, T is above 1.96 or 2. So this is very statistically significant at the 95% level. And so now we can interpret it. So for every 1 unit increase in temperature, sales increase by 0.014 now that we have controlled for dissimilarness. So now this represents a more typical sales pattern without the holiday season, where as things get warmer, people tend to go out and shop more in the summer and in the spring than they do in the winter, except for the holiday season. So now we've pulled out that dissimilarness, so we really do have the effect of when things get warmer, what happens to sales, holding everything else we can think of constant. So by controlling for dissimilarness, the sign flips. Now we have a positive slope on our best fit line. So what we see is that every 1 degree increase increases sales by $0.014 billion, which is $14 million for this hypothetical company. So we're also able to include other independent variables if we need to control for other effects. We call them control variables. So you're not limited to just one. In fact, you're going to want to include every single one that you need. So you'll ask yourself, is there anything else correlated with X and Y that I need to control for? And if there is, you pull it out and put it in the model. Then you ask, is there anything else? So sometimes you may have 2, 3, 4, 5, 6, 10 control variables depending on your particular question. So a control variable is an independent variable, meaning it's not the dependent variable. It's on the right-hand side of the regression equation. And it's included in your statistical test, but the goal is to control for some other factor that is not your primary factor of interest. So this is not the thing we're going to interpret. This is not the effect we care about. This variable is in the model just to give us a clean, unbiased estimate of the effect of x1, our first independent variable, on y. Okay, so the estimation of a multivariate model follows the same steps as the OLS bivariate model. The reason we went through all of that at the beginning of the semester, chapters 1 through 4, is to help us get comfortable with the model and how everything works. And now we're going to be able to add these other variables. But it's analogous to what we did in chapter 3. So here is another regression, and it's one we've done before. We've done the effect of height on wages several times, but now many times when we talked about that regression, we talked about the fact that there's a lot of endogeneity here. There's a lot of things that could be correlated with height and wages. One of those things is adolescent height, right? If you're taller when you're younger, then your adult height is likely to be higher, and your wages are likely to be higher. If you're in athletics, right, maybe that means you're otherwise tall, you're a leader, you know how to manage your time. There's a lot of things that could be correlated with athletics, and that's obviously correlated with height and wages. And then whether you're in clubs at school, right, that also could be correlated with wages. I'm not so sure on adult height, but we'll just go with it for now because this is the example that Bailey picked to start with here. So let's see how that changes. So here we have our bivariate regression that we've seen a bunch of times before, right? This is the one right here. We've looked at several times the effect of height on wages, that bivariate regression. It is statistically significant, and if it was unbiased, if we didn't have these z's that are probably correlated with x and y, then we could interpret it to say a 1 unit increase in adult height leads to a 0.41, I think this was dollars per hour increase in wages. It's an increase because it's positive. Well, what about this first regression? So this first one is only adult height and adolescent height. It is not including athletics and clubs for this first multivariate regression. So this one, if it was unbiased, we could go up here and say, is it statistically significant? It's not actually. It's not statistically significant. So we cannot interpret this coefficient. Then we add another control and look also, we add 2 more controls, athletics and clubs, and what we see is we're also not statistically significant. So this is one of the trade-offs we're going to face here, is when we want to control for things, sometimes by controlling, our statistical significance goes down. But that's okay, because remember, we can't even trust this t-value because it's probably a biased regression. And the t-values, the interpretation of those, requires that you first be unbiased. So in Model A, well, I already went through all this, but in Model B, by controlling for athletics and club membership, neither beta 1 nor beta 2 are statistically significant. But again, we don't really care that much about beta 2. We're not going to be interpreting it. It's just there to get us a good estimate of beta 1. So now let's go through and think about how this affects some of our formulas that we've already learned in terms of the sum of the squared residuals. It does modify things a little bit. Intuitively, you can still think about a line going through a cloud of dots, but now the cloud of dots is not necessarily on a two-dimensional plane like this. All right, so this is the way we've been drawing it, with y over here and x down here, and we've had our best fit line going through, right? You can still think of that as the analogy, but the issue is that now with 3 variables, we're actually in a 3-dimensional space, and you're going to see my drawing skills fall off pretty quickly when we move to 3 dimensions. Not that they were great before, but let's say this is x1 and this is x2. So now this is a cube filled with dots, all right? And there's still going to be a line going through the space, but it's going to minimize the distance to this cloud of dots, more like a literal cloud now than before. It was a cloud, quote unquote, but it was on a flat surface, right? It was on a plane. We could draw it on the board. Now these dots fill kind of a cube if there's 2 right-hand side variables, and the best fit line comes through it. And I'm not going to be able to draw that very convincingly, but you get the idea. But it's still about the slope of the line, all right? It's still the slope given the x and y axis. So we can still think about it in terms of that 2-dimensional picture when we're trying to intuitively understand what's going on. So now let's go into a little bit of the math of this. So here's our old friend, the residual. Remember, the residual is just the difference between the actual value of y and the fitted value of y. And remember, the fitted value was take the regression coefficients that you get, plug them into the regression equation for beta 1, for beta naught hat, beta 1 hat, beta 2 hat, ever how many betas you have. And then for any values of x1, x2, x3, again, ever how many you have, it will tell you what the expected value of y hat is, the fitted value. And so the residual was just the difference between the real value of the dependent variable and that fitted value of the dependent variable. It's the distance of the dot from the line, just like it always was before. Again, you can think about it, just go back, sorry, that's supposed to be y, and this is x. So you can still think about it in terms of the distance of a particular dot from the line in terms of the y-axis, that distance, all right? That's the residual. of course, now again, it's in that cube. So just imagine a lot of dots floating in a cube. That's your scatter plot, and there's a line going through it, and it has a slope still. It has a rise over the run. As you move across the x1 axis, 1 unit, it will go up or down or stay flat on the y-axis. All right. So the residual is still the distance of the dot from the line. So again, you don't really have to be too worried about that three-dimensional way of thinking about it, because metaphorically it's the same as it was here in this 2-dimension. It's the distance of the dot from the line. That's the residual. Okay. So what we need to do now is we need to plug in our value for y hat. So y hat, again, is just the regression equation, but with the fitted value, with the estimates, sorry, of the intercept, the slope for x1, the slope for x2, all the way to the slope for xk, the last control variable in the regression. All right. So we plug that in for the fitted value. We've done all of this before. We did it back with the bivariate regression, but I'm just going to update you now as to what it looks like for the multivariate. So then we need to square it, right? So because it's the sum of the squared residuals. So this is just squaring the residual. So I just took this expression for the residual, and now we are squaring it right here. That's this outer parentheses here. The parentheses that's here, oh, everything doesn't highlight. Here and here, this parentheses, that's what's squared. So multivariate OLS finds the betas, all of them, that minimize the sum of the squared residuals. Just like in the bivariate case, it found beta naught and beta 1 that minimized the sum of the squared residuals. It's still the best fit line. It's still the line that goes through the cloud of dots with the least amount of error, where the dots on the whole are as close to the line as possible. All right. Now we're not going to do this ourselves. We're going to let the computers do the work. The computer doesn't have to fit a line a bunch of times. There is a formula for this, just like there was a formula for the bivariate regression. And we will get to that in a later screencast. So that's it for this first screencast. In the next screencast for section 5.2, what we're going to do is we're going to look at why this is called omitted variable bias. And we're just going to get very, very precise about what that means. We're going to have a little bit of math notation, but it's going to give us a much better way of thinking about when there is bias. In other words, when this picture is not correct, and instead what we have is maybe a beta, our true beta 1 is over here, and the mean of the distribution is here, right? This is the mean, the expectation of this distribution. What problems does that cause us? And we'll be able to say that very precisely now, because we now will have all the machinery we need to talk about that. All right, that's it for the first screencast. Talk to you guys later.